We then come to June 2009, paper 1, and an experiment again. This time Desmond carries out an investigation into the relationship between the current flowing in a metal wire and the voltage across it. A graph obtained from Desmond's results is shown below. So we've got voltage, current. What does this graph show about the relationship between current and voltage for this metal wire? Straight line through the origin. That means that the voltage is directly proportional to the current. Voltage is directly proportional to the current. Now, if we have a direct proportionality, that means if we double the current, we will double the voltage. So you can see there 0.11, 0.22, 0.44. So every time we double the current, we double the voltage. And that's a feature of a directly proportional straight line through the origin graph. During the experiment, Desmond switched off the current between one reading and the next. Why was this necessary? Now this goes back to the very first experiment that we were talking about. This is to prevent the temperature increasing, and that's the temperature of the wire. So to prevent the temperature of the wire increasing, or to prevent the wire from heating up. It's better to say the temperature of the wire increasing. So to prevent the temperature of the wire increasing. On the same grid, carefully draw the straight line which Desmond would have obtained for a wire of double the resistance. Well, if he's double the resistance, then that means if you consider R is equal to V over I, for the same current, to get double the resistance you need double the voltage. So it would need to go through 2 and through 4 and be a straight line through the origin. So we need, with a ruler, to draw a straight line like so. Now there's 2 marks there. One mark I would assume is for getting it to be steeper, and the other for getting it to be actually 2 times steeper, but that's what you require. So it needs to go through the 2, through the 4 and through 0, 0 to be a straight line through the origin with twice the gradient. The resistance of a piece of wire depends on several factors. Does the resistance of the metal increase, decrease, or remain the same when these things happen? Okay, so this is about resistivity, and remember the resistance depends on the length of the wire, it depends on the cross-sectional area, and it depends on the material. So when the length increases, the resistance of a copper wire increases. Correct. Longer wire, greater resistance. When the cross-sectional area increases, the resistance of a copper wire decreases. Bigger cross-sectional area, easier for the current to flow along. The last one then, a piece of cotton thread and a copper wire have the same length and cross-sectional area. Which one of the following statements? The copper wire's resistance is bigger, smaller, about the same as the cotton thread. Well, the cotton thread isn't a conductor, and therefore its resistance should be bigger than that of the copper. So the copper wire's resistance is smaller than the cotton thread. The cotton thread is a material which is a non-conductor, so shouldn't conduct. So length increases, the resistance increases. When the cross-section area increases, the resistance of the copper wire decreases, and the copper wire's resistance is smaller than that of the cotton thread, allowing it to be a conductor. We'll come back then to some calculations involving resistor networks. This time we have 2 resistors in parallel with a third resistor in series, a 12-volt battery connected in. We're asked first of all to calculate the total resistance of the circuit, and we have to show we're working out as per usual. Again, we're going to start by focusing on this parallel part. Because we have 2 resistors in parallel, then we can say that the resistance of that parallel network is equal to the product, so that's 20 times 30 over the sum, which is 20 plus 30. So that's equal to 600 over 50, 600 over 50, which is equal to 12 ohms. So we get 12 ohms there. Oh. 12 ohms for the parallel part. and then the total resistance is going to be equal to 12 plus 24, which is equal to 36. Okay, so the answer, the overall answer is 36 ohms. And just be careful not to do what I just did and answer the question too early. Calculate the voltage across, the next part is calculate the voltage across the 24 ohm resistor. Well, in order to calculate the voltage here, what we need to know is we need to know the current flowing around it. So we can calculate the current flowing around, we'll call that current I, by using the total resistance into the total voltage. So I is equal to V over R, which is equal to 12 divided by 36, which is equal to 0.33 amps, or a third of an amp. Then we can now work out the voltage across here by saying V equals IR. The same current goes through there, so that's 0.33 amps going around that circuit. Therefore, we can now say V equals I times R, so that's equal to 0.33 times 24, which is equal to 8 volts. So the voltage across the 24 ohm resistor is 8 volts. And that's the final question. Thank you for listening, and I hope you've enjoyed that. I hope you've learned something as well.